characterized by a surface, overlapping surface between the two conductive layers, the top and the bottom, and this surface is A. The green is the dielectric. And the distance between the two conductive layers could be referred as D. Okay. Now, what is the electrical capacity of this transducer? The electrical capacity of this transducer is given you by this very well-known formula. C, the electrical capacity, is given by epsilon times A over D. Okay, in which epsilon here is the dielectric constant. Okay, A and D are the geometrical parameters. Okay, once again, A is the surface of the overlapping surface between the conductive layers, and D is the distance between these two conductive layers. Okay, and epsilon is the dielectric constant that is characterizing your material between the two conductive layers. Okay. So, what is the general working principle of this capacity transducer? The general working principle is that if we link one geometrical parameter of this capacitor, okay, let's say the area or D, the distance, to whatever displacement by using a proper mechanical link, as we already saw before, then we are changing the geometrical properties of this capacitor. And therefore, by measuring the change of the capacity, we can refer to the change of, let's say, the distance D or the area A. Okay, and thus we can go back to the physical quantity that we want to measure. Okay, so as a general working principle, we can, for example, measure the change of the distance that through mechanical links is representative of your unknown motion, okay, through the measure of the change of the capacitor, okay, as well as we can measure the change of the overlapping area between the two layers through the measure, once again, of the change of the capacity. Okay, by the way, in order to measure the change of the capacity, so we need to measure the capacitor of this electrical characteristic. This could be measured by what is called bridge. Bridge measuring circuit. Okay, we will see something about the bridge measuring circuit when we will deal with the strain gauge measurements. Okay, but now just let's consider enough to say that this is a special electrical circuit that is capable to measure very, very small variation of your electrical quantity. Okay, and so we can use this bridge circuit to measure the change of the capacity of your capacitor. Okay, why we are expecting this change? Because these geometrical properties, could be D or could be A, are related to your unknown physical variation of the distance, for example, the motion or whatever. Okay, so as we saw together when referring to the potentiometer, there is a mechanical link between the properties of your capacitor, D on A, and the actual motion. That's it. Just one more information concerning the equivalent impedance of this electrical parameter. So the electrical impedance is a measure of the resistance, okay? This impedance is given by 1 over 2 pi f c, in which f is the frequency of your current of your electrical circuit that is flowing, okay, and c is the capacity. So as you can see, z for this kind of electrical parameter is very, very high. Generally, okay. Why that information is very important for us? Because if you go back here at the very basic, okay, in order to measure the change of the capacity so that you can estimate the unknown physical quantity, you need to measure that. So as you remember from the potentiometer measuring circuit, okay, you need something to measure the change of the capacity through, for example, a bridge circuit. And therefore, the information that the equivalent resistance, that is the impedance, is very, very high, is important to set up the proper measuring circuit, the proper bridge measuring circuit in order to have the information of the change of the capacity. Okay. That's it for this kind of transducer. Okay, so once again, we are able to measure motion, displacement, linear or angular, depend on just on the mechanical link that you have between your actual physical quantity and the geometrical property of the capacitor. And this information is estimated through the measurement of the variation of the change of the capacity, okay? Because we are changing D or we are changing A, okay? Measuring circuit, a little bit more attention because the impedance is high, very, very high, generally speaking. For example, if you are measuring continuous current circuit, then F, the frequency, is 0. Therefore, Z is infinite. Okay, so it is just an open circuit. Okay, that is very, very important. On the contrary, if you are having this high frequency signal with high frequency content, then F is very, very high. Z, the impedance, start having low values. Okay, smaller values. Okay, C, the capacity general is of order of pico. Okay, so 10 to minus 9 to minus 12. Okay, so it's very, very small, generally speaking, and therefore you have to take into account that C is very, very high because also of that. Good. The next transducer is the piezoelectric transducer. So once again, we would like to have the measurement of displacement, generally speaking. Okay. The other method is, the other transducer is the one that is using the piezoelectric material. So the property, the physical property associated with piezoelectric material. And then let's see what's about. So first, what is a piezoelectric material? What are the main parts that represent the piezoelectric materials from the chemical point of view? So the piezoelectric crystal is made by mainly quartz, okay, or barium titanate. As main components. Then there are other smaller parts component that make difference, but these are the main components. So what is the piezoelectric effect now? So these materials are available naturally. Okay. So what are, you can mine them, yeah, not to produce them by yourself. Okay, generally. So what is the piezoelectric effect? The piezoelectric effect is that is capable so PZT, piezoelectric effect, okay, will produce an electrical field when the material, the PZT material, of course, changes dimensions. As a result of an imposed mechanical force. Okay. So this is the PZT effect. So we are stressing the material through an external force, okay? Because of that, the material is changing its dimensions. And from the electrical point of view, what's happening is that the material reacts to this change of dimension by creating some charges, electrical charges somewhere in the structure, so that we can collect a differential potential with respect to different points. Okay, so the electrical field. Because of external force, you are, like, for example, pressing the table like this, okay, there is very small changes in dimensions. Okay, you are not do not wait for, say, expecting kilometers, okay, just microns. Okay. This is the PZT effect, the piezoelectric effect. You have also an opposite effect, okay, that is the electroactuation. Small changes. Okay. The electroactuation effect is just the reverse. Of the previous effect. Okay, so we are setting the material with a differential potential with an electrical field somewhere. Because of that, the material is reacting to this electrical field, okay, through a change of dimension. And this change of dimension is capable to, let's say, produce a force onto something external. Okay, so it starts change. Okay, I don't know if you are aware, for example, some smart controls that are going to be introduced in the aerospace field are based on this electroactuation effect, okay? But also the reverse, that is the PZT effect. Now, concerning, this is general, concerning our transducer, okay, so concerning the piezoelectric transducer that is capable to transduce displacement, okay, what we are having here is that the working principle is that first we are having a force F, okay, that produce a crystal deformation Oh my God, I forgot to start recording. Sorry. You have to remind me. Okay, sorry for this delay. I'm now start recording from now on. I'm sorry for that. What we saw before is another displacement transducer that is called capacity transducer. This capacitor is based on the evaluation, the capability to sense the change of the capacity because we are changing some geometrical property of the capacitor, mainly the distance or the overlapping area between the conductive layers. Okay, in order to do that, we have to use what we call a bridge measuring circuit. And we have to remind that the impedance, electrical impedance of this transducer is generally very, very high. Then we are talking about PZT transducer, piezoelectric transducers, and these are based on the piezoelectric effect. This piezoelectric effect is the one that will produce an electrical field when the material, the crystal, is subjected to a change of dimension as a result of an imposed mechanical force. The reverse effect is called electroactuation effect. And this electroactuation effect is just the capability to have a change of dimension, therefore a capability to excite whatever external system with a given force because we are exciting your PCT crystal through an an electric field. Okay. So for our purposes, the transducer works in this way. So first, we are having a force that produces a crystal deformation, okay? Then what's happening according to PCT effect? The crystal deformation induce an electrical charge. Somewhere in the surfaces of these crystal, these piezoelectric pieces. Then, last step from the working principle point of view, such a charge is harvested. By a specific conductive layer. And thus, finally, producing the output tension. Let me call that E output. Okay, so this is the general working principle. Now let's see the layout, the general layout of this PCT. So I can start drawing the conductive layer. That is capable to harvest the electrical charges. Then we have, yeah, just to make it readable. We have the PZT material. Okay. And then at the bottom, we have once again the conductive layer. Let's say like this. Okay, the piezoelectric material is characterized by a thickness T. Okay, so what's happening is that, as I just told you before, we have this piezoelectric crystal in a shape of a prism, like in a parallelepiped, for example, then is excited by an external force like this. Okay, we are compressing, for example. Okay, as a result of this external force, the PZT material is changing its dimension. And from the material point of view, this change of dimension is producing an electrical, redistribution of the electrical charges that are all harvested here by these conductive layers. Thus, what we have to do is simply collect these charges at the bottom and the at the top, for example, and then have the output tension EO like this. Okay. Whatever. Okay. In our analysis, because we are interested in the transducing opportunity of this material, PZT material, okay, this working principle could be used either to measure displacement, as we can see, okay, or we can measure the force, okay. That is one other option that we can have. Now, a very, very simple equation. What is the relation between the source of the effect? The PZT effect is having the force as the input. Okay, so my source, the input is the force, the output is the electrical charge. Okay, so what is the relation between these two input-output quantities? Okay, the relation under certain circumstances, and we are in those circumstances, is a linear one. Okay, so what I can say generally is that if we refer to or a direction that is orthogonal to a plane, okay, to a surface that is given by the conductive layer, okay? So if I define the charge, change the charge Q that is collected by a conductive layer whose normal is pointing at the ith direction in your whatever reference free system, and we compare this with the input force, okay, that could happen in a completely different direction, let's say Fj, okay. These two quantities, the input, the force at a given direction, and the output charge harvested by a plane oriented in a other I direction. Therefore, we have that these two are related by this very nice formula, okay, in which the Kij is generally called as PZT constant, okay. Qi, once again, is the charge, the electrical charge. That is harvested on a plane whose orthogonal axis points the I direction. Okay, and of course, F is the force in the whatever J direction. Okay, so this is a very nice relation, a linear relation, okay, that could be very helpful, okay, when designing such a kind of transducer. The missing part now is the relation between what I'm measuring and what is my output and my input. Okay, so the output is the output tension, is not the charge. Okay, whereas the input could be the force or whatever displacement. Okay, so we can say that if we drop all the indexes, let's say we are referring to two different orientation, two different directions, okay, I, J, whatever, just to be easy. Then what we can say is that the Q is equal to KPF, just the same as before. I'm dropping the directions. I know what are the directions that I'm considering, but now just removing that from the notation. And therefore, what I can say is that the output tension, it could be proved that, I'm not going to do that with you, is given you by SB PT. That is the output tension, the one that I'm going to measure. I'm going back to the drawing here. Okay, so the output tension E0 that I'm going to measure is dependent, linearly dependent, okay, from the one geometrical parameter of the PCT, the thickness, okay, and external forces. That is here in that notation given by the pressure. So once we know the area, you have the force as well, okay, here. And SV is the tension sensitivity. Sensitivity. Okay. P is the applied pressure. Okay, T is the crystal thickness. We already mentioned that. Okay. And this equation is very, very nice. Why nice? Because it's a linear one. I like that. There is just one internal parameter, that is the tension sensitivity. Okay. And thus we can use this PCT just by having the geometrical parameters prescribed, so I can measure the pressure through the evaluation of the tension, the output tension, or if I have just a preload already there, I can measure the change of the thickness, so the displacement, through the measure of the output tension as well. Okay, so we can use this transducer in both ways. Okay. By the way, we are using this transducer mainly for forces, mainly for pressures. Okay. So the thickness is considered constant because the variation of thickness is very, very, very small. So it's not that useful to use this transducer as a transducer of the change of dimension, so displacement. However, it could be used. The main objective of this transducer is to have a load, so pressure. Okay. Just to give you numbers, the quartz, the material quartz, is generally considered with dimensions thickness of about 1 millimeter. This is the typical dimension. Generally, the tension sensitivity, SV, is about 0.05 volts over meter over Pascal. Okay. So just to give you a number, if you are having a 1 megapascal pressure on the conductive layer on the crystal, so if P is equal to 1 megapascal, so not that large pressure, it means that the output tension, the one that you are going to measure, is given you by SPT numbers, and that is about 55 volts. Okay, that is a very, very large number, therefore continuous current. Okay, just to have you an idea. There are additional effects that are very important to take into account. I'm not going to take into account right now, but just I would like to mention that there exists what is called the shear sensitivity. That is, we have not to consider just compression, okay, but also shear sensitivity, okay, and we have to use that. We are not going to use that. The equations that are useful for us are just the ones that I give you. But just to mention that there is a shear sensitivity, and we have to introduce more complex equation. But, and that is important for me, the working principle is always the same. Okay, so what is changing is the complexity of the equations that we have to consider. It is important to be sure that the effect that I show you is not the only one. There are more effects, shear, for example, and then we have to take into account. If you want, it is just saying that when we were referring to the simplification here, where I drop the indexes here at this point, okay, actually what I have to do is to consider the full tensor of the PZT property. So K Ij should be considered as a full matrix, okay, 3 by 3, for example, okay, 3 direction of possible orientation planes and 3 direction of possible excitation forces. Okay, so we have to consider. Okay, is that okay for you? Today we have just 1 hour. Is that true? Okay, so we have about 8 minutes left. So I owe you about 15 minutes. Okay, so that's it for today. So I still owe you about 7 minutes. Okay, and see you Monday. Sorry? I don't know, because it depends on the program. As long as we are going on with the program, then we have material to go down to the laboratory. Okay, I think that in a 1-2 weeks time, we can have our first laboratory. Yeah, classes, standard class courses, okay, and in a 1 or 2 weeks time, 2 weeks maybe, we can go down in the laboratory, having our first laboratory experience. Okay, any questions from remote, from home? Yes? Yeah, you can use that. You can use that. The working principle is this one. As you can see from the picture. So the problem is just to have a proper information of the actual force or pressure that is acting on your PCT. So is it for used for liquid motion, for pressure, or whatever? Doesn't matter. It is just a mechanical problem, not a transducer problem. Okay. Any other question? Okay. That's it for today. Have a great weekend. Enjoy the not that bad, the good weather in Rome. But however, see you on Monday. Bye bye. Thank you.
Arrivederci, professore.
Ciao.